Okay, welcome back. During the break, I sorted out that it's exercise 6, where you were doing the experiment with the code, the running time of code, and then yeah, you have this question of if your processor throttles, you are violating this, so you're probably going to come to a crap conclusion because you were nowhere close to the assumptions of the test. Just do it on desktop. But yeah, otherwise, good data, good experiment. These two should be sorted out, we hope. And then we saw these two for the t-test as assumptions. They're pretty common in statistical tests because, like I said, there's a lot of data out there that's normally distributed. That's good. Not every group, pair of groups has the same variance, but if you're not sure, if you're kind of doing the experiment to see if these two things are the same or different, it's not unreasonable that they would have a pretty similar variance. But how do we know? Okay. Oh, sorry. I guess, yeah, representative of the population, fine. Yes. Independent, identically distributed does probably deserve a little explanation. Yeah, it's just, I have my data points, and if it's basically like if I tell you like, hey, data point I-1 was this, if that gives you any information about data point I, they're not independent. And then again, if you just have two different populations, you kind of smash them together in the experiment, probably not from the same distribution, and we should be careful about that. So normally distributed equal variance. This is harder. If you want the honest answer, once again, we never know the true distribution. What I actually do and what most statisticians actually do and most people who do data analysis actually do in practice is look at the histogram and see if it looks about right. These seem probably pretty reasonably normally distributed. Let me let's just get them a little farther apart there. Like the orange lines here, they're not a perfect normal distribution, but they are data that is really sampled from a normal distribution. Do they have equal variance? Well, like if I just kind of look at how wide the histograms are, yeah, it looks about the same. I would do a t-test on this data, and I would never look back. Maybe you don't like that. Maybe you want to be a little more careful. Maybe there's times you want to be a little more careful. It turns out there are statistical tests for this, which is, it is backwards from most statistical tests where the null hypothesis is what I want. I'm hoping that the distribution is normal. So just because of the way the math works here, we assume it's normal, and we see if it are we going to prove that it's not, or we'll have to find out. But again, the assumption that we're rejecting is that the data is normal. So now we're hoping for a big p-value, not a small one. Usually we're hoping for a small p-value. Yes, that thing I just said. And yeah, there's a thing for that. It's satisfied normal test. What's my import here? Okay, so then, okay, before I do a t-test, if I'm being sort of maximally careful, and let's come back to the X and Y data. I just want to be consistent at what I'm looking at all the way through. I no longer care about that. I no longer care about that. Okay. So I'll check these. And again, I guess what I really care about is the p-value. And okay, this is a good example, right? Like this is totally dependent on my random sampling here. 100%, absolutely, no question, this was sampled from a normal distribution, but the p-value is pretty small. It's not less than 0.05. So in neither one of these cases would I reject the null. And so I guess I would kind of, okay, I guess, again, I can't ever prove the null to be true. That's not how the statistical test works. But this is like, well, I guess it seems kind of probably maybe normal, good, close enough for me to continue. And then I can do this t-test with like a clean conscience. Look at that p-value and find out that it's quite very small. I don't like the sentence. I have to soften the sentence because frankly, this is often not reasonable. Here, you know, it's one thing to look at a distribution and say, yeah, it's kind of balanced and kind of vaguely normally shaped and pretty similar variances. But of course, that's not all data. Sometimes I have data that is just like crazy, not normal. Like it just looks very different. Like, and if I do something like this, these are now my data sets, right? Like, again, I'm making fake data, so I'm allowed to make different fake data. These don't look normal. They look quite asymmetric. An imbalance like that is definitely one of the things that normal distributions don't do. Normal distributions are inherently symmetric. So I'm pretty suspicious about this. I get pretty small p-values. So this is saying, well, it's pretty unlikely that those were drawn from a normal distribution. It would be weird for those to be drawn, like sampled from a normal distribution. And that can happen. And of course, it can be a bit of a judgment call sometimes. If I do the test here, I'd find two small p-values. That's probably what I expect. The other thing we're assuming here is equal variance. I learned the word homoscedastic for this course. That's exciting. It sounds super smart if you say that. So this is now I have the same sort of question here, which is, well, are they equally like spread out? Well, again, I have a pretty good idea here because I'm cheating, but there's a test for that too. It's Levine's test for equal variance. This takes two things, right? Because I'm comparing two samples to see if they have the same variance. For the normal test, I'm looking at one at a time. Again, I care about the p-value much more so. Oh, good one. Again, a small p-value. Actually, wait, no. I would expect these to have a different variance because they're bigger numbers and I've cubed them. So that's actually probably what I would expect. Because I've messed with this data so very much. So now, again, truly, genuinely normal. This is kind of what I expect, right? Right down the line, big p-values because I have mathematically guaranteed these two assumptions. Sure. Yeah, I guess once again, these this equal variance test is run backwards. It's the null hypothesis is the thing I'm hoping for, so I'm hoping for a big p-value. And this data on the slides, I got a small p-value. So now I'm kind of suspicious that these two things do not have the same variance. Maybe I should be careful about putting them in a t-test. And for my y, and maybe I didn't point out here, I have like in the slides, I have the x pair of data and the y pair of data that are kind of continuing through here if you're kind of lost on what's happening. These were the two that seemed like they were probably not normally distributed, but they do seem like they maybe probably have an equal variance. And yeah, that's exactly what happened. I did genuinely sample these first two from a normal distribution, but with a different variance. And these other ones I sampled from some completely different probability distribution, but with the same variance. Well, with just a straight up same distribution. I just shuffled one over so it looked maybe visually different. So I could look at histograms for this. I could, I guess, in the case of the t-test at least, the default t-test assumes the equal variance on the two groups. There's another different t-test, Welch's t-test, that does it. So I can do the exact same thing. I'm sure, I keep meaning to do this. It would take a while. Okay, so because I've had students ask, like, why don't we just always say this then, right? Why don't we just always turn off the equal variance assumption? Because then we're never violating that assumption if it's not there. And the answer is going to be like, look, the more you tell the test, the more, the more you're giving it about your data, the more likely you are to actually come to a conclusion. So if I leave this as true, and it is true, if the two groups do have equal variance, a little bit more likely to get a small p-value there, which is what I want. So what I think is, if I went looking hard enough, if I really explored and spent a lot of time, making up random data sets and fiddling with them, I'm sure I could come up with one where equal var equals true gives me a p less than 0.05, but equal var false is a little above 0.05. Like, I'm sure those data sets are out there. I've just never bothered to play around and find them. So, be honest with yourself, be honest with the math. So, like I said, what I would actually do in reality, and what people who actually analyze data seem to do, is look at the histogram and say, does it look kind of pretty normalish? Yeah, so it's probably fine. We'll come back a little bit more to what probably fine means. But maybe if it is truly pathological, like, what did I have there? I had a gamma. That's pretty different, right? It's got a longer right-hand tail. I'm gonna, I'll be willing to bet that's not quite a perfect normal curve shape. But maybe we can make it happen. So transforming data is something, and again, like a lot of these things, you maybe should be a little bit suspicious of. You should think about whether this is the right way to proceed or not. But take all your data and pass it through some function. So that might be like, everything gets squared, everything gets square rooted, cubed. And that will reshape the distribution because of those aren't linear functions. Maybe you can guide it towards being a more normal shape. In this case, no. Like here, I squared everybody. That didn't help. Oh, but if I take a log of every data point, that seems like it helps. And I'm pretty sure in this case, it's because the log gamma distribution is normal, citation needed. So that, again, is much more normally distributed. It looks balanced. It looks symmetric. It looks pretty equal variance. Like, maybe the blue is a little more spread out. Hard to tell. But definitely more like a normal distribution. It actually passes the normality test now. Again, I get large p-value, so I don't have to reject the assumption that they're normal. Every little while I get a question from a student that's like, oh, can I just transform one group this way and another group a different way? No. Like, if you're looking for, are these values the same or different, it makes absolutely no sense to do different things to each group. You could add 10 million to a group and then find out that those numbers are bigger. It's not meaningful. If you're going to transform data like this, probably you're going to want a monotonic function, because otherwise, again, you're kind of moving data past itself. Maybe you want to be invertible. What happens sometimes is, like, within a community, like within some field that always works with this kind of data, people who work on that kind of data know that it makes sense to square it because of something they know or has been worked out about the data set. I can definitely imagine something where it's like, if what you're measuring is a length, but what you care about is the area type of thing, it totally would make sense to square it, because length squared is probably proportionate to the area, where length is not by itself. So if I have some good reason to think I care about this and I'm measuring that, and here's how they're different, or here's how they're related to each other. In general, okay, let's look at log, because that's the one that we had a couple slides ago. So the data back here a few slides is right skewed. And what that means is there's more of a tail hanging out here on the right-hand side of the histogram, right? So the sort of, well, sorry, the original data was this. The way in which it's not symmetric is that there's more stuff way out on the right. That's right skewed. So something like a square root or a log, something that is like, if you graph that function, it's concave down, might be useful. If it's the other way, if there's a tail on the left-hand side, some function that's concave up is going to help, exponential or x squared. It can be worth a shot. So there's a few things happening here. Maybe that, I just have some transformation that makes sense to me and makes sense for my data. And then all of a sudden, like, things look totally normal and I'm happy and I can move on. I also imagine if I tried hard enough, I could come up with some very pathological data set where if you square everything, the means change position. That's totally a thing that can happen. So you probably want to be careful here, but it's a thing people do. If they're not, so don't come into this in this sort of very quantitative way that I can hear you thinking you want to do, which is, if the normal test fails, I must stop and I must fix it, maybe by transforming the data. If the data is close to normally distributed, we can just do a t-test. This normality test is a tool that we can use to evaluate how we feel about the normality of this data. It's not it's not like this should go in an if statement. Nice. This is just inferential stats coming back to bite us, right? Oh, sorry. Dang. I thought I had such a good example there. I just had the wrong data. We'll have an example of that later then. Yeah, it's interesting how often, well, because it's presumably about 1 out of 20th, 1 out of every 20 times I do a thing, I expect a small p-value just by chance, right? Less than 0.05. And yeah, quite often you get there. That's how that goes. That's just how stats does. Oh, maybe it's a log Pareto distribution that's normal, whatever. So again, for data like this is one where I would not do a t-test here. This data is too weird and too pathological and nothing in any way like a normal distribution. I can't do a t-test on this. That's not reasonable. What I have is a really, really long right tail. So I probably want to do something like take the log or take the square root of that. If I do the log, maybe it's a log Pareto that's actually a normal distribution. Please don't quote me on these things. I don't live in probability distributions. This, like I said, I'm at 50 data points on either side. This now looks quite symmetric, very much like it has equal variance. I would totally happily do a t-test on this. I could, if I felt the urge, do the normality and equal variance tests. I honestly probably wouldn't. It happens they pass here because they should. For the data set I have, or like the data set that I randomly generated when I created these slides, I can then, on the logged version of the data, do the t-test, and I get a nice small p-value, which suggests that the means of the underlying things are different. That's probably not a surprise because I did sample them from slightly different distributions. So that's the game we're playing here. How much time I got? Okay. All right. And actually, maybe we'll do this. Here's what happens for the rest of stats, which will take another, well, nicely into next week. Basically, some more tests with the commentary that goes around them is what's happening next. So we have Well, this is actually not true, right? Because we've seen the normality and equal variance test, but those are a little more like utilities, right? They're not the star inferential stats that we need or that we're going to come to conclusions with. We really have the t-test so far, at least for us. And again, there's assumptions that are pretty good assumptions. They're pretty useful. They're often true, but not always. The big one that is almost too big an assumption to even mention is that there's two groups. Again, I have men and women. I have SFU and UBC, or I have whatever two halves of the world we're going to look at here, and that the thing I'm measuring is sampled on for group A, the thing I'm measuring is sampled from a normal distribution, and from group B, the thing I'm measuring is sampled from a normal distribution. They're probably not the same distribution. In fact, I'm hoping they're not, but that they do have equal variances. Assume the means are equal, proceed. A small p-value tells you that that probably wasn't true, and reject the null. Good. These two, normality and equal variance, fine, sure. They are useful tools to kind of give us some insight into our data. Again, we're guessing the underlying distribution. We do our best. We make our best guess. What if I have more than two? What if I'm measuring height, because we all know people have heights. What if I have three groups instead of two? Or 4 or 5 or 6 or whatever. Well, that's, I just said right back here, that's not what the t-test does. But you are a clever programmer, very good. One thing you could do is just do a bunch of t-tests, right? If I can do the t-test between two groups, well, I can just do all pairs, right? The n choose 2 version of this. And I can ask, well, are these saying those are different, those different? Let's find out. But we remember what we're doing here, which is every time I do a statistical test, I look at that p-value. There simply is, like, even if again God comes down and tells us the null hypothesis is true, there's still a 5% chance of getting a small p-value, because that's what that number is. It's what it's there for. So if I do a bunch of t-tests, that starts to pile up on itself. So the probability here is the probability is 0.95 of a small p-value actually meaning what I interpret it to mean, that the means are truly different. And so what's the probability of that happening 3 times in a row? Well, it's 86%. That's still pretty big number, but it's not the one I said, right? I said back here, alpha is 0.05. I'm going to look for a p less than 0.05. Only 5% chance of incorrectly rejecting the null hypothesis. But that's not what happened. What I actually had was a 14% of incorrectly rejecting a null hypothesis, because that's how this goes. That sucks. I don't want that. I don't like this. This number starts to sound pretty high, right? I'm very likely to go around rejecting my null. So there's a couple ways to deal with this. The easiest and most obvious is the Bonferroni correction, which is, once again, something that I feel like is so obvious. It only needs a name so I can kind of cite it. It needs a name so I can say why I'm doing this thing. But it's basically, if I'm doing 20 tests and I want alpha equals 0.05, I divide that by 20 and I look for p less than that. Effectively, I'm just spreading out my probability of failure across all my things, right? So if I want, again, I'm willing to accept a 5% probability of coming to an incorrect conclusion. Well, if I'm doing m tests, I'll just divide by m and put my, 1 over m of my probability here and here and here and here and here. Sure, that's totally a thing I can do. I will say Bonferroni correction to make me sound like I know what I'm doing and indicate that why I'm doing it. And then I can do this thing. I can do many t-tests and look for p less than 0.05 divided by however many things I just did, and I can be honest with myself, right? That's totally reasonable. And this always works, right? You can do this, so you know, no matter what I'm doing. But if I have a t-test situation, there's a whole separate stats test for that, where if I have many groups, the analysis of variance test, is it Z distribution? Probably, is basically this. It's the same, like I have decent data. Every group is normally distributed. All the groups have equal variance. So if I do that, fine, I can do an ANOVA. So that's why I have more than one. Maybe I want, maybe I'll do 4 groups here. Maybe I'll tighten them up a little bit. Let's do that. Yeah. So this one, like, yeah, it seems pretty clear that the red bars are a little bit to the right of everybody else, but it's hard to really tell what's going on here. Well, again, if I scroll there, I definitely believe these are normal equal variance. If I scroll there, do I believe it? And I think I would look at this and I would judge that all 4 groups are probably equal variance. I feel good about that. Each histogram is kind of equally wide. They all seem reasonably symmetric. They all have like at least a vague shape. If you look at the green bars here, or again, apologies to anybody colorblind, it doesn't really look super normally distributed. Just an accident of the samples. I could, you know, I could do all of these normality tests if I want to. Can I give? I legitimately don't know if I'm allowed to do this. Yup. Let's not just throw numbers into a thing. Yes, I can give any number of samples there. Okay, so I can do that. I am reasonably happy here, right? That these things, I was reasonably happy when I looked at the histogram too. I could, I guess, do this. Do I want to do this? How bad a thing have I set for myself here? I've got 4 choose 2, 6. Fine, I guess. So I could do okay. Boy, this is some good content. What did I just say? I should have 6 of these. So Y, Z, and Z. So there's the first 3. And then YZ. Yeah, okay. What have I learned? I don't know. I just did 6 statistical tests. I got some pretty small p-values. Again, these are times 10 to the negative something or other. I am looking, so I just did 60 tests, right? So I should be comparing to this. I am looking for p less than that number. Are they? So this one isn't. So that's what, times 10 to the 8 times 10 to the negative 3. So all the other ones are small enough. Okay, I can do that. Like, that's totally fine. That was a bit of a pain in the butt. What I should do, and what I would much rather do, and is much more fun and easy, is an ANOVA. Oh, it's the F stat. Sorry, the Z stat is the t-test, but for different than 0. So yeah, the reason this is called F one way is because the underlying probability distribution for an ANOVA is the F distribution. It is not otherwise a very evocative name. But I can do this, and this is much more fun. As long as I spell everything right. Yeah, okay, so I got a small p-value here. So again, this is a p-value I'm comparing to 0.05. I'm ignoring that stuff I did up there. This is just this, and this is a very small number. right? Times 10 to the negative 20. So what's happening here is I'm very confident that this is not by chance. Again, the question I've asked is, let's assume that all 4 of these things were drawn from the exact same distribution with the same mean. Well, from distributions with the same mean, and I also assume they're normal, or they're equal variance. But yeah, assuming these means are equal, would it be weird to get this result? And the answer is, yeah, it'd be super weird to get this result if all 4 of those had the same mean. And that's a who cares, right? Because that thing I did up there was at least told me something. I don't know who. Like, all I know is the means don't seem to all be the same here. It doesn't tell me anything about which one. So now that I've done this and I've said, oh, look, small p-value, there's some differences in here. The next thing that happens is called a post hoc analysis. And it's basically somebody, like, I'm not going to manually do this, but so the tool is going to manually say, okay, well, here's how these things compare, and here are the ones that seem to be different, and here are the ones that no conclusion. So there's a couple of these post hoc tests. I'm choosing Tukey's honest significant difference test because it's honest. So I write the name. And then it's in, right, that's not the link I should put there. There is a thing in stats models for it, so it's a different package, right? So just on the like straight up technical side of things, all of this was in the SciPy package. There's a separate stats models package because, you know, different authors, different world, they expected the data to be different, so we're going to have to rearrange things. I'm just going to do that. We'll see what it looks like. Well, okay, so what I have here are just separate data sets, right? I just have data sets 1, 2, 3, and 4. What the I don't know, the stats model style or whatever, I expect to have all of those things sort of piled on top of each other in a single column, and beside that, which group did this come from label. So if you happen to have a data frame and everything happens to be the same length, and because of course in data frames all columns have to have the same number of data points, I'm going to do something different over here, and I'm not going to have that, right? So yeah, in fact I do. I have different sized sets of data, so this won't work. But if I do have this case, I can melt. Melt is the opposite of a pivot, so instead of having separate columns for each thing, I'll have column for the data and a column for which subset it came from. And this is what I need for Tukey's. Then I can do the thing. Okay. So over here, we do all that. We forget. How do you spell? That's probably how you spell Bonferroni. There we go. Now, okay, I have a small p-value. Now I want to do this. So again, what I need to do is get all of these things together. And this is one of those moments in this course where I'm like, well, I could plan ahead and I can write the code, but I'm like, you know what? That's not how that goes. But now I'm screwed. How do we do this? I am gonna have to think about this for a second. Okay, so what I need to do is I need to look at like the size of W. And I need like that many. Okay, right, there's a Python way to do this. Okay, so this can go there. And then I want to like stack all these together. Okay. So my goal here is to create, again, the column of labels, which is going to be the thing it came from, and then the column of data, that's just the thing. And now what I've got to do is I've got to do this for everybody. Like I've got a stack for these on top of each other, but then I'll have like, here's all my W's, here's all my X's, here's all my Y's. So what I'm going to do is pause the recording while I do that, because nobody wants to watch me type all that. Okay, we got there. So it turns out, right, so because I did this thing with a Python list, I had to join them like their Python lists, which is just a plus sign. And then because these things are NumPy arrays, I had to join them like their NumPy arrays. But that's all I did. I created a like, you know, length of all of these things combined column of labels. And then beside all the letter W's is a data point from set W. Beside all the X's is X. Great. This is the shape I need. I have labels and data. Great. Okay. Now I can do this. Wait, I have to actually. Okay, I put it in a data frame because what the heck. Okay. And I called them different things here. I called them label and data. And then I also have to give the alpha here because the post hoc analysis is going to be like, it's going to take care of this for us. It's going to check like, oh, is the p-value less than alpha or not? I have to print it. Okay, and now what I get is for groups, for W and X, we reject the null and we conclude that these two groups, oh, sorry, we do not reject the null. As far as we know, like we don't know anything about the relative means of those. For all of the other pairs, we do reject the null and we come to the conclusion that these seem to have different means, be less than 0.05. I want more false in there. I'm gonna have to, I'll probably do it. So again, the true underlying distribution here, they do not have the same mean. But of course, I don't get to look at that. I just have to look at the data. And based on the data here, assuming we're going to get there in a moment. Yeah, okay. So yeah, these two, W and Y and X and Y, I know that somebody in there, both of them, I guess, have different means, but the data isn't there to come to that conclusion. So I do come to the conclusion that W and Z, basically, I guess, as it is here, it's Z has a different mean than everybody else is the effective conclusion. I really care about this column. The other things here are the sort of allowable, like the confidence interval or whatever it is. So like if I subtract the X's, the W's and the X's from each other, what's the sort of confidence interval on where those means are? Well, it's somewhere between here and here. And basically, if 0 is in this range, I'm going to see a false here. Oh, sorry, yeah. And if 0 is not in this range, that must mean the means are different, so I'll see a true there. But again, well, I really care about this reject column, not the rest. There is there's a thing I can do, which is plot them. You know, the plot's a nice visualization. It's not really, what the hell just happened there? Okay. Like, because again, I don't know why. I've seen students kind of peering at this diagram and trying to line something up. No, like this is the thing. This is the actual quantitative thing. This is a nice visual, I guess. Like, I don't know if you have what your opinion is about this visualization, but I think it's a nice visualization of what's going on there. So after all that, again, I get to see what's going on here. Well, I get a quite good, right? Like, then again, I snuck in a weird truth here that's just a little bit different. If I don't know what's going to happen there. But what I see is some combination of conclusions. In fact, the exact same combination of conclusions in this data. Yeah, so I narrowed this. I have a smaller variance, so these error bars shrank. But still, as far as we can tell, X and Y might have the same mean. The mean is somewhere on that line. So they might be there, and all three of these might have a mean there with the confidence I'm willing to give this. Okay, what do we got? About 10 minutes left. Yeah. Okay. I said earlier today that I'm suspicious when somebody comes at me with a one-tailed test, and the one-tailed test is this one, or of course the opposite, which is the null hypothesis is asymmetric, and therefore the conclusion is asymmetric. Because, like I said earlier, this assumes that group one will never be less than group two. That is not a conclusion. If that's true, I'm uninterested in it. So, okay, maybe this, right? Maybe if it's a case like this, it's like, well, if the profit stays the same or gets worse, that's the I don't want to do that case. The profit gets higher if I do the thing, put the thing on sale or redevelop, or refresh the user interface of the software or whatever the thing is here. Okay, then I only care about this conclusion. I do not care about the other half. And I think that might make sense here, but you are presupposing which direction your thing is going to go. The other reason this is a little bit suspicious is you are effectively doubling your p-value, because again, the story here is, okay, well, I'm gonna do the experiment, and I'm going to look at how weird that outcome was, and if it was really weird under the assumption of the null, I'm going to reject and take the alternate hypothesis. So back in the picture of what a student's t-distribution looks like is, on the two-tailed test, I reject if my t-stat is over here or if it's over here. On the one-tailed test, I'm only rejecting on this side, so I just have less area here. Which means in order to get 5% of the area, my t-stat moves back the other way, and I effectively have made it easier to come to that conclusion because I have half as many ways that things can be weird, if that makes sense. There is a thing, like, I didn't point at it, but there's the, what kind of alternate hypothesis are we looking at here? It's two-sided, or it's I'm looking at the less than case or the greater than case, like whichever direction I want to push that one-tailed test. Again, it can do that. It can do that calculation for you. I'm just suspicious of it. So again, if I'm doing the one-tailed test, it's basically the two-tailed test with double the alpha. That's really tempting. It's really tempting to be able to lie to my audience that way. It's another reason I'm pretty suspicious about somebody doing a one-tailed test. Doesn't mean you can't do it. Doesn't mean the stats police are going to come and arrest you. It just means that you should think pretty carefully about it, probably. You should be able to justify it. Maybe that's what I mean. If somebody is about to do a one-tailed test, okay, what I expect is a paragraph explaining why you've decided that's okay and why you're not lying to me here. That's what's in my heart, I guess, if I see a one-tailed test. So yeah, effectively you get to double the p-value. And you can do that, maybe I should say that right. You can do that manually. Like, you can put this alternate argument on the t-test, but if you kind of don't have a test where that's a thing, you can effectively just make sure the thing is going the right direction. It's not the mean is bigger, the mean is smaller, and then double your alpha. You can do that. Don't use the one-tailed test to pre-decide this is how my experiment is going to go, so I'm only going to look for that result. Then you're just lying with a bunch of math hiding it. All right, that's a great spot to stop, and we're a little early, but the hell with it. I'm going to call it a week, and I'll see you on Friday. Otherwise, we continue as we were. Have a good week, everybody.